tab that somehow sharing debugger is there, but there we go. Whoops. Oh, where did you go?
That's it.
Anyway, in the wiki, there's a video link under class links, second link under class links. There we go.
Okay.
Artistic style was just my sneaky way.
And then give it to Matt because he's a control freak and he'll get upset if...
Okay.
So, welcome back everybody. Thanks for coming, and I hope you had a good
Also
week.
the,
Had a fun time playing around with artistic
Cables
style.
are better for that side of the room.
All right, so we're recording.
Nice.
I guess we should get things started.
I
then.
do have mini news.
All right. Perfect.
I'm connected with Jeremy on LinkedIn now.
Oh.
Ooh.
Wow.
Not sure how we can
We
use
are-
that going forward.
You
but
out of how many people is he connected to?
Probably quite a few, I think. But I've been trying to connect because I thought I'd try and get him to talk about something in the last one, but it didn't work out.
No, yeah.
I tried to spam him on his GitHub thing.
Did you ever get a
the other-
response?
Well, now we're on LinkedIn, so now I can just message him on LinkedIn.
Okay.
Yep. Do you get a response?
definitely
I haven't tried
Yeah.
messaging him afterwards
Yeah.
on LinkedIn, so.
I mean, does anybody here read their LinkedIn messages? I don't know.
I actually do.
I do.
Sometimes I do.
But I'm
I do.
looking for a job.
Oh, yeah, that'll do it.
Yeah.
That's all the news I had. Was.
All
Oh,
right.
that's cool.
Well, if we have anything we want from Jeremy, we know who to go to.
Yeah,
So now
hopefully he'll answer.
I'm second to Jeremy now. I guess. That's nice.
Yeah, see?
We all are. We all are, yeah.
2 degrees of separation away. How exciting.
This is a big day.
Okay, yeah, we are connected, so I'm good. I thought I might be a third connection, but I'm second as well.
Yeah.
So that's good.
And three
Alright.
connections, probably lots of other really cool people. I don't know who's connected. I can only imagine they're probably smart. I don't know.
Yeah. Yeah. If you connect with Jeremy, you'll be second You'll be second to many very smart people. Good point.
That's how it begins.
Okay. Anything else?
Any other announcements or news? Okay. Should we test Andrew?
Yeah.
Andrew.
Andrew, if you've made it this far, what should we get him to type into Slack? Say something. Just mention this in the Slack
Yeah.
channel
Yeah.
that we're testing you.
Yeah.
Just say that you've passed the test.
Yeah. Type beers.
Do not take beers.
Oh.
That just
Well, it's Piers.
it invokes the
But is it invoked on the Fast AI
Oh,
Advanced
maybe
channel?
not. Maybe not. Yeah.
So
We can only hope.
We can test.
try it.
Well, let's let Andrew
Okay.
test.
Yeah.
Okay. Let's start this.
So, welcome back everybody. Thanks for coming, and I hope you had a good week and had a fun time playing around with artistic style. I know I did. I thought I'd show you. So I tried a couple of things myself over the week with this artistic style stuff. I just tried a couple of simple little changes which I thought you might be interested in. Yeah. Oh, actually, yeah. Okay. So
Can you turn it up a bit?
one thing before I talk about the artistic style.
Do you know how?
Well, you guys are 1.5. I've been listening at 1.25, which is almost like a regularly fast talking. This is definitely more.
You need to do the function key.
Yeah,
I maxed it.
it's mostly good.
Did you?
Every once in a while,
Really?
it's a
Maybe
little
this thing
funny.
has its own volume.
Oh,
No,
yeah,
he
it does.
just maxed it
Oh,
while
it
you
does.
were going around the table.
Go ahead.
He just maxed it while you were telling.
I just want to point out some of the really cool stuff that people have been contributing over the week. If you haven't come across it yet, be sure to check out the wiki. There's a nice thing in Discourse where you can basically set any post as being a wiki, which means that anybody can edit it. So I created this wiki post early on, and by the end of the week we now have all kinds of stuff with links to the stuff in the class.
I feel that it's a bit too much. I suggest to move one step.
1.25
That's 2.5?
1.25 sounds pretty
Just
basically
saying he
normal.
made a wiki forum post.
You get used to it at one.
I can imagine.
You just need to give
I
yourself
listened to the
Sometimes
first
you
40
miss-
minutes of 1.5. I don't remember it sounding like that. But anyway,
Should
you know,
we give it
this is
another
it's
chance?
pretty lightweight stuff. I'd vote for 1.5
Sure,
for
yeah,
a while. Until he starts saying
let's go for
something.
5 minutes of 1.5 and see if it becomes normal.
I like it.
Can't wait to
Where
hear
you
what
take
conversations like afterwards.
Examples, list of all the links, code snippets, a handy list of steps that are kind of necessary when you're doing style transfer, lots of stuff about TensorFlow Dev Summit and so forth. Wiki threads every week, so look out for that. Lots of other threads. One I saw just this afternoon popped up, which was great, from Chin. Talked about trying to summarize what they've learned from lots of other threads across the wiki. And this is really, sorry, across the forum. This is a great thing that we can all do is, when you look at lots of different things and kind of take some notes, if you put them on the forum for everybody else, this is super handy. So if you haven't quite caught up on all the stuff going on the forum, looking at this curating lesson-based experiments thread would be probably a good place to start. So a couple of little changes I made from my experiments. I tried thinking about why, quite a few of you pointed out how depending on what your starting point is for your optimizer, you get to a very different place. And so clearly our convex optimization is not necessarily finding a local minimum, but at least saddle points it's not getting out of. So I tried something which was to create take the random image and just add a Gaussian blur to it. So Gaussian filter is just a blur, and so that makes the random image.
I have a comment.
Yeah.
Is it, does it make sense to say that he has a convex optimization and he's finding saddle points?
No, I was
Doesn't
thinking the
make any
same
sense.
thing, right? So his claim previously that it was a convex problem was
Contradicting
just
himself.
wrong.
Yeah.
He's contradicting
But he's
himself.
sticking to the convex optimization. He's sticking to his point.
Yes,
Okay.
yes.
He's consistently wrong.
Yes.
Give him that.
Into this kind of thing. And I just found that even the plain style looked a lot smoother. So that's one change that I made, which I thought worked quite well. Another change that I made, just to play around with it, was I added a different weight to each of the style layers. And so my zip now has a third thing in, which is the weights, and I just multiply by the weight. So I thought that those two things made my little bird look significantly better than my little bird looked before, so I was happy with that. You could do a similar thing for content loss. You could also maybe add more different layers of content loss and give them different weights as well. I'm not sure if anybody's tried that just yet.
You know, why are there 5 style layers? In the
So,
resolution?
he pulls the weights off of, or the outputs from 5 layers. Like, he doesn't just take the last one, he takes some from each.
0 on 5.
Yeah.
Which sort of makes sense, that you're gonna want some really fine details, but you're also gonna want some less fine details and some coarser ones. So for example, in Starry Night, you've got the swirly stars that are kind of like this big, but you're also gonna have brush strokes which are like that big. That's my take.
Mm-hmm. And it makes sense to weight them too. That,
Yeah.
although that would take a lot of experimentation.
That's just experimentation. Right?
Okay.
Yes, Rachel.
A question? I have a question in regards
Do
to
you wanna
data
take
transfer
those?
for cartoons.
Yeah,
Cartoons.
I should.
You're synchronized.
Yeah, that's awesome.
Team.
Didn't even talk about it. Boom.
When we think of transferring the style, what we really need is transferring the contours of the cartoon to redraw the content in that style. This is not what style transferring is doing here. How might want to implement this?
Yeah. I don't know that anybody's quite figured that out, but I'll show you a couple of directions that may be useful.
There's the, and yeah, I've tried selecting activations to correspond to edges and such as indicated by one of the column visualization papers and comparing outputs from specifically those activations.
Yeah. So I'll show you some things. I'll show you some things you could try. I haven't seen anybody do a great job with this yet, but here's one example from the forum. Is somebody pointed out that this cartoon approach didn't work very well with Dr. Seuss, but then when they changed their initial image not to be random, but to be the picture of the dog, it actually looked quite a lot better. So that's one thing you could try. There's some very helpful diagrams that somebody posted, which is fantastic. They're summarizing what we learned. I like.
Why wouldn't you always initialize for the content anyway?
I was wondering that too.
Yeah. It seems like the obvious.
Yeah.
Yeah.
When is it ever going to be better to not do that? Oh well.
I concur.
It's a good question.
Okay. We all agree.
But you've seen that there were other options like initialize with a style, initialize with a... So,
Just random with Gaussian blur. Yeah.
so technically speaking, it depends. Like maybe if the style and image are somehow distant from each other, then maybe initializing somewhere in between would be closer to the final result. But so I think it was just a set of experiments, and they found out that obviously initializing from the original picture works best.
Yeah.
But he has never said that.
No.
Just a couple of minutes ago, in that somebody summarized, and they were like, choose the best starting point. Start with the image. Start like it was just 2 minutes ago in a video.
Oh, it was in text.
It was in text.
And in the summary there, they said that it was best
Yeah,
to start with
they said that they tried different starting points, but I don't know. The summary was not shown. It was shown like what experiments they were doing.
Oh, I see. Okay.
Okay.
This summary of what happens if you add versus remove each layer. So this is what happens if you remove block 0, block 1, block 2, block 3, and block 4 to get a sense of how they impact things. So you can see for the style that the last layer is really important to making it look good, at least for this image. One of you had some particularly nice examples. I love this. Like, it seems like there's a certain taste for kind of figuring out what photos go with what images. I thought this Einstein was terrific. I thought this was terrific as well. Brad came up with this really interesting insight that starting with this picture and adding a style to it creates this extraordinary shape here where, as he points out, you can tell it's a man sitting in the corner, but there's like less than 10 brushstrokes. So sometimes this style transfer does things which are surprisingly fantastic.
Looks like more than.
I have no idea what this is even in the photos, so I don't know what this is anything either, but I guess I don't watch that kind of music enough. So there's lots of interesting ideas you can try, and I've got a link here, you might have seen it in the PowerPoint, to a Keras implementation that has a whole list of things that you can try. Here are some particular examples. This is something called, and all of these examples you can get the details from this link. There's something called chain blurring, and for some things, this might work well with cartoons. Notice how the matrix doesn't do a good job with the cat when you use they call it classic, this is our paper, right? But if you use this chain blurred approach, it does a fantastic job. And so I wonder if that might be one secret to the cartoons.
Yeah.
Chain what?
Chain blurring.
Can you go
Chain
back
blurring.
1 second?
He doesn't, his image covers it up. Oh, boy.
Uh-oh.
Uh-oh.
It's a little tricky. There must be a hotkey to go back 10 seconds in YouTube. Alt,
Yeah, the
arrow
left
or something?
arrow.
Oh, just left arrow does it. Okay,
Oh,
beautiful.
I learned something.
That's good to know. I will say, back in the day when this first came out, I did a lot of experimentation with it, and I did a lot of the classic versus the MRF. MRF was always way, way better. It doesn't look so great here,
This
but
cat doesn't look very good.
yeah, but everything I tried it on was much better. This chain thing, I've never tried that. That looks pretty awesome, actually.
I think it was Matt who brought it to the meetup, and he's been showing the result. Was it you?
No.
When we, like the paper reading group, that was me.
Can you back
Yeah,
up
but-
another 5? I want to get the GitHub link.
Somebody has brought it on the phone showing like that it does. Was it you?
Can you move the?
It was
On the
you.
phone?
IT.
I didn't do it on the phone, no, I did it on the desktop.
Thank you.
I think it was before your time. It was a long time ago.
Okay.
Yeah. Oh, good, you're writing down the URL, so you'll figure out what the chain thing is and tell the rest of us?
Sure.
Thank you.
Nice
Okay,
follow there,
thank you.
Bruce, that was good.
Matt's a control freak, I'm the delegation freak.
And we're off.
Job with the cat when you use they call it classic, this is our paper, right? But if you use this chain blurred approach, it does a fantastic job. And so I wonder if that might be one secret to the cartoons. Some of you I saw on the forum have already tried this, which is using color preservation and luminance matching, which basically means you're still taking the style, but you're not taking the color. And I think in these particular examples, this is really great results. I think it depends a lot on what you strike with.
So, what? Can you go back 5 seconds? So, how do you do that? Like, how do you just take the color, or what does he take? Luminance matching? Is it just, do you process the output from the layer to just keep the luminance? I don't know how actually you would, I mean, I sort of guess, but I'm not gonna get it.
You add a penalizing term for when the colors change. I don't know.
Maybe. Maybe. So output with color preservation. Oh, color transfer, luminance.
He calls it
Match.
color transfer but luminance matching. So it sounds like it's two different things because
Yes.
luminance matching sounds like what we're doing just with the style, style matching, right? It's just similarly you're just creating like a penalized cost function. But then this color transfer something different.
Yeah. So say for luminance matching, I guess I could imagine, so you're pulling out all these things out of the style network, and you could just calculate their luminance, and that's the only thing that shows up in your loss function, and then
Yeah.
just preserve the other stuff.
I see, yeah.
Yeah. Okay.
Well, there's something interesting here. You can see the Van Gogh-ish brush strokes here, whereas here it doesn't look nearly
And for
as.
Andrew,
Yeah.
who's not going to watch it here. Versus here.
Oh, yeah, that's right.
Yeah.
But remember to shut that program down cleanly at the end of the night.
Yeah. Yeah. Okay, ready?
Ready?
Particular examples, this is really great results. I think it depends a lot on what things you try with. You can go a lot further. For example, you can add a mask and then say just do color preservation for one part of the photo. So here the top part of the photo has got color preservation and the bottom hasn't. That's pretty cool. They even show in that code how you can use a mask to say one part of my image should not be stylized. Again, get the results. What is really crazy, use masks to decide which one of two style images to use. And then you can really generate some creative stuff. So there's a lot of stuff that you can play with, and you can go beyond this to coming up with your own ideas. Now, some of the best stuff, you're going to learn a bit more today about how to do some of these things better. But just to give an idea, if you go to likemo.net, you can literally draw something using 4 colors, and then choose a style image, and it will turn your drawing into an image. Basically, the idea being that blue is going to be water, and green is going to be foliage, and I guess red is going to be foreground. So there's a lot of good examples of this kind of neural doodle, they call it online. Something else we'll learn more about how to do better today is if you go to outlinelayer.com, there's a very recent paper called Pix2Pix, which is basically, we're going to be learning quite a bit in this class about how to do segmentation, which is where you take a photo and turn it into a colored image, basically saying the horse is here, the bicycle's here, the person's here. This is basically doing the opposite. You start by drawing something, saying, I want you to create something that has a window here, a windowsill here, and a door here, and a column there, and it generates a photo, which is really remarkable.
That's really
Okay.
It doesn't end up looking as nice as that.
No, it often
I've played
doesn't.
around with it quite a few times, and
same.
none of them looked as nice as the original image.
Okay.
And
I feel better.
I just found the paper from the color preservation, and all of his sample images are from an actual paper. It's not some student just playing around.
Oh, I was thinking, these students are incredible.
Does anybody want me to post the paper?
Sure.
Okay.
Yeah, I tried just putting like a window on there, and it's like it doesn't even look like just a window. It does like all this other stuff. It's nothing ends up being as nice as that.
You just did one big window.
I was like, oh, what if I do one? Well, I tried doing stuff like this with lots of boxes. It didn't look really great. I'm like, well, what if I just do one window? Well, this one window, the only thing I put on there looked a lot like a window, and it did look like a window, but not as nice as this stuff.
It would have taken a lot of work to set up all those boxes and label them and I don't know what.
Yeah, I also didn't have as much patience for that size.
No kidding, yeah. I would have hit the random button.
So the stuff we've learned so far won't quite get you to do these two things, but by the end of today, we should be able to. This is a nice example that I think some folks at Adobe built, showing that you could basically draw something and it would try and generate an image that was close to your drawing where you just needed a small number of lines. Again, you can find this, we'll link to this paper from the resources. This actually shows it to you in real time. You can see that there's some new way of doing art that's starting to appear where you don't necessarily need a whole lot of technique. I'm not promising it's going to turn you into a Van Gogh, but you can at least generate images that maybe are in your head in some style that's somewhat similar to somebody else's. I think it's really interesting. Okay. One thing I was thrilled to see is that at least 2 of you have already written blog posts on Medium. That was fantastic to see. So I hope more of you might try to do that this week. Definitely doesn't need to be something that takes a long time. I know some of you are already also planning on turning your forum posts into blog posts. So hopefully we'll see a lot more blog posts this week popping up. I know the people who have done that have found that a useful experience as well. So one of the things that I suggested doing pretty high on the list of priorities for this week's assignment was to go through the paper knowing what it's going to say. I think this is really helpful. It's when you already know how to do something, is to go back over that paper, and this is a great way to learn how to read papers, right? Because you already know what it's telling you. This is like the way I learned to read papers was totally this method. So I've kind of gone through and I've highlighted a few key things which as I went through, I thought were kind of important. So in the abstract of the paper, let me ask, how many people kind of went back and re-looked at this paper again? A few of you, that's great.
Nobody.
So in the abstract, they basically say, what is it they're introducing? So it's a system based on a deep neural network that creates artistic images of high perceptual quality. Okay, so we're going to read this paper, and hopefully at the end of it, we'll know how to do that. Then in the first section, they tell us about the basic ideas. So when CNNs are trained on object recognition, they've got a representation of the image. Along the processing hierarchy of the network, it's transformed into representations that increasingly care about the actual content compared to the pixel values. So it describes the basic idea of content loss. Then they describe the basic idea of style loss, which is looking at the correlations between the different filter responses over the spatial extent of the picture mass. And this is one of these sentences that read on its own doesn't mean very much. But now that you know how to do it, you can read it and be like, oh, okay, I think I see what that means. And then when we get to the method section, we learn more. So the idea here is that by including the feature correlations, and this answers one of the questions that one of you had on the forum, by including feature correlations of multiple layers, we obtain a multi-scale representation of the input image. This idea of a multi-scale representation is something we're going to be coming across a lot, because a lot of this, as we discussed last week, a lot of this class is about generative models. And one of the tricky things with generative models is both to get the kind of the general idea of the thing you're trying to generate correct, but also get all the details correct. And so the details generally requires you to zoom into a small scale, and getting the kind of big picture correct is about zooming out to a large scale. So this was one of the key things that they did in this paper, was show how to create a style representation that included multiple resolutions. And we now know that where they did that was to use multiple style layers. And as we go through the layers of EGG, they gradually become lower and lower resolution, larger and larger receptive fields.
So that's
Always great to look at.
his algorithm for understanding a paper is basically, it's really great to understand the paper first and then go and read the paper. It seems backwards.
Yeah.
You should,
How do you do that without a class? Or
you should already
teacher?
know the paper before you actually attempt to read it.
Well, no, he's saying that here's how you learn to read papers. If you know what it's telling you, then you can learn to recognize the markers for the important things in the papers. You know what's important. You read the paper, you say, okay, that matches with what I think is important. You're going, okay, that matches.
It's still,
And something that's implicit here is he's saying, all those equations, those aren't important.
okay, I see. Yeah, I get that. That's a better way of explaining it than how he explained it, which is more, well, you need to understand it first and then you can read it.
Yeah. And understand it in his terms is like implement the code,
Yeah.
Yeah.
which for me is like the last level of understanding, not the first. Plus, I don't know if he's actually suggesting that highlighting papers is a good way to, I don't know, retain them or something. I think it's really terrible myself.
I think his basic idea, especially because with nowadays things, you do not need to have a real detailed understanding of what's going underneath in order to implement the system, doing something. But in order to implement it, one has to follow all of the steps, like data preprocessing and data transformations and blah, 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 blah. And once you've done it, usually inside of our head, we now know the steps. We now know that there were certain parameters, like for example, there was optimizer, there was something else, there was something else. And then when we read the paper, we find that familiar things we saw. And we can kind of have the association, and we can now understand that what's behind it better than when we're just reading the paper. Because I've seen it multiple times, when you're just reading the paper and when you kind of hear somebody talking on something totally unknown, it might sound very logical, it might sound very convincing, it might sound very good. But if you really have knowledge of that topic, it doesn't sound that convincing anymore, because you know where the some things are cut and so on and so on and so on. So I think his idea is that you try to implement it so that you will have some anchors that then you will be able to get more from paper.
And he mentions goals, which I'm sure everybody does. You start with the abstract, well, is it interesting? And he skips to the end and go, did they have really good conclusions? If so, okay, I'll look at the paper. And if the paper looks confusing or if it gets really detailed in math, then he goes online and hopefully somebody's written a blog post already. And he's like, oh, here's an example. I don't think it's here coming up. Oh, here's a nice example, plain English. Oh, this is great. And then can go back to the paper and dive
Yeah.
a bit more.
Yeah.
Seems like a good cheat.
Seems like the paper should just be written in a way that you didn't have to do all those steps.
You
Initially.
would think so.
Papers didn't always. I don't know, but I heard that scientific papers like 30, 40 years ago used to be written in a much different style than they are now. It wasn't so dull. It was more kind of like Bruce looking. Right?
I don't
I think
remember
they're
that.
mostly always been terrible.
Yeah.
There's a few writers who are really clear and they've written classic papers, and your best source is to go back to the original paper. But so many, it's
I bet there's sample bias.
there's sample bias.
That people say, oh, all these papers from 30 years ago that I read, they're awesome papers. And the ones now are horrible. Well, that's because you read the awesome papers from 30 years ago. You didn't read the schlock.
Right.
So old timers say no.
Yeah, okay, timers say no.
The figures to make sure, and I was thrilled to see that some of you were trying to recreate these figures, which actually turned out to be slightly non-trivial. So we can see exactly what that figure is. And if you haven't tried it for yourself yet, you might want to try it, see if you can recreate this figure. Okay. It's good to try and find in a paper the key finding, the key thing that they're showing. In this case, they found that representations of content and style in a CNN are separable, and you can manipulate both to create new images. Yes, okay, hopefully that, now we can look at that and say, oh yeah, that makes sense. You can see that with papers, certainly with this paper, there's often quite a lot of introduction that often says the same thing in a bunch of different ways. So it's often worth, the first time you read it, one paragraph might not make sense, but later on they say it a different way and it starts to make more sense. So it's worth looking through the introductory remarks maybe 2 or 3 times. You can certainly see that, again, talking about the different layers, how they behave. Right, again, showing the results of some experiments. So again, you can see if you can recreate these experiments, make sure that you understand how to do it. And then there's a kind of whole lot of stuff I didn't find that interesting until we get to the section called methods. So the methods section is the section that hopefully you'll learn the most about reading papers after you've implemented something by reading the section called methods. Now I want to show you a few little tricks of notation. You do need to be careful of little details that fly by. Like here, they use average pooling. Okay, so that's a sentence which if you weren't reading carefully, you could skip over it. Now we know, okay, we need to use average pooling, not max pooling. So they will often have a section which explicitly says, now I'm going to introduce the notation. This paper doesn't. This paper just kind of introduces the notation as part of the discussion. But at some point, you'll start getting Greek letters or things with subscripts or whatever, notation starts appearing. And so at this point, you need to start looking very carefully. And at least for me, I find I have to go back and read something many times to remember what's L, what's M, what's N. Okay, this is the annoying thing with math notation is they're single letters. They generally don't have any kind of mnemonic. Often, though, you'll find that across papers in a particular field, they'll tend to reuse the same kind of English and Greek letters for the same kinds of things. Right? So M will generally be the number of rows. Capital M. Capital N will often be the number of columns. K will often be the index that you're summing over, so on and so forth. So here, we've got the first thing which is introduced is X with an arrow on top. So X with an arrow on top means it's a vector, right? It's actually an input image, but they're going to turn it into a vector by flattening it out. So our image is called X. And then the CNN has a whole bunch of layers, and every time you see something with a subscript or a superscript like this, you need to look at both of the 2 bits, because they've both got a meaning, right? The big thing is like the main object. So in this case, a capital N is a filter, and then the subscript or superscript is like in an array or a tensor. In Python, it's like the thing in square brackets, right? So each filter has a letter L, which is like which number of the filter is it. And so often as I read a paper, I'll actually try to write code as I go and like put little comments so that I'll like write layer, square bracket, layer number, close square bracket, and then I have a comment after, say like N, L, just to remind myself. So I'm creating the code and mapping it to the letters. So there are NL filters. We know from a CNN that each filter creates a feature map, so that's why there are NL feature maps. So remember, anytime you see the same letter, it means the same thing within a paper, not necessarily across papers. Each feature map is of size M, and as I mentioned before, M tends to be rows and M tends to be columns. So here it says M is the height times the width of the feature map. So here we can see, okay, they've done dot flatten, basically, to make it all one row. Okay, now this is another piece of notation you'll see all the time. A layer L can be stored in a matrix called F, and now the L's got at the top. Doesn't matter, same basic idea, it's just an index. So the matrix F is going to contain our activations. And this thing here where it says R with a little superscript, this has a very special meaning. It's referring to basically what is the shape of this. So when you see this shape, it says these are R means that they're floats. And this thing here means it's a matrix. You can see the X, so it means it's rows by columns. So there are N rows and M columns in this matrix. And every matrix, there's one matrix for each layer, and there's a different number of rows and a different number of columns for each layer. Okay? So you can basically go through and map it to the code that you've already written. So I'm not going to read through the whole thing, but there's not very much here. And it'd be good to make sure that you understand all of it. Perhaps with the exception of the derivative, because we don't care about derivatives because they get done for us thanks to the Arno TensorFlow. So you can always check the bits about derivatives. Okay, so then they do the same thing, basically describing the Gram matrix. So they show here that the basic idea of the Gram matrix is that they create an inner product between the vectorized feature map I and J. So vectorized here means turned into a vector. So the way you turn a matrix into a vector is flattened. This means the inner product between the flattened feature maps. So those matrices we saw.
Pause.
Yeah, so
it's a little bit of a digression. I don't know if you saw that Google put out a package a couple of days ago which will do the derivatives explicitly for you, so you can separate them out. So if you want to actually see what the derivatives are and play with them and pull out intermediate results and stuff.
That's that TensorFlow?
I don't even think it's
It's like symbolic.
I think it's symbolic differentiation basically, but they've added a little bit more on it.
Rather than Mathematica, it just gives you the result, and then you have to spend time to work out where the result came from.
Yeah, but I guess it's, you know, it's all in Python code, and you have this sort of forward pass
Yeah.
that defines, you know, things, and it, for each of the backward
that
steps,
gives you
it
this-
tells you. Yeah.
What's the package called?
I can't remember. I'll find it though and post
Oh,
it.
well,
Yeah, it looked kind of cool.
yeah. That's cool.
So hopefully you'll find this helpful. You'll see there'll be like small little differences. Rather than taking the mean, they use here the sum, and then they kind of divide back out the number of rows and columns to kind of create the mean this way. In our code, we actually put the division inside the sum. So you see these little differences of how we implement things. And sometimes you may see actual meaningful differences, and that's often a suggestion of like, oh, there's something you should try, you know, some differences you could try. Okay, so that describes the notation and the method, and that's it. Right? But then very importantly is throughout this, anytime you come across some concept which you're not familiar with, it'll pretty much always have a reference, a citation. Right? So you'll see there's little numbers all over the place. There's lots of different ways of doing these references. But anytime you come across something which has a citation, like it's a new piece of notation or a new concept, you don't know what it is. Generally, the first time I see it in a paper, I ignore it. Right? But if I keep reading and it turns out to be something that actually is important and I can't understand the basic idea at all, I generally then put this paper aside, put it in my to-read file, and make the new paper I'm reading the thing that it's citing. Because like very often, a paper is entirely meaningless until you've read one or two of the key papers it's based on. Sometimes this can be like reading the dictionary if you don't know English. It can be like layer upon layer of citations, and at some point you have to stop. I think you should find that the basic set of papers that things refer to is pretty much all stuff you guys know at this point, so I don't think you're going to get stuck in an infinite loop. But if you ever do, let us know in the forum, and we'll try and help you get unstuck. Or if there's any notation you don't understand, let us know. Another of the horrible things about math is it's very hard to search for. You know, it's not like you can take that function name and search for Python and the function name instead of some weird squiggly shape. So again, feel free to ask if you're not sure about that. There is a great Wikipedia page which lists, I think it's just called math notation or something, which lists pretty much every piece of notation. There are various places you can look up notation as well. Okay, so that's the paper. So let's move to the next step. So I think what I might do is kind of try and draw the basic idea of what we did before so that I can draw the idea of what we're going to do differently this time. So previously, now this thing is actually calibrated, you'll be pleased to hear, we had a random image and we had a loss function. So it doesn't matter what the loss function was, right? We know that it happened to be a combination of style loss plus content loss, right? And what we did was we took our image, and our random image, and we put it through this loss function, and we got out of it two things. One was the loss, and the other was the gradients. And then we used the gradients with respect to the original pixels to change the original pixels, right? And so we basically repeated that loop again and again, and the pixels gradually changed to make the loss go down. So that's the basic approach that we just used. It's a perfectly fine approach for what it is, and in fact, if you are wanting to do lots of different photos with lots of different styles, like if you created a web app where you said, please upload any style image and any content image, here's your artistic style version, this is probably still the best, particularly with some of those tweaks I talked about. But what if you wanted to create a web app that was a Van Gogh irises generator? Upload any image, and I will give you that image in the style of Van Gogh's irises. You can do better than this approach, and the reason you can do better is that we can do something where you don't have to do a whole optimization run in order to create that output. Instead, we can train a CNN to learn to output photos in the style of Van Gogh's irises. And the basic idea is very similar. What we're going to do this time is we're going to have lots of images, right? And we're going to take each image and we're going to feed it into the exact same loss function that we used before, right? With the style loss plus the content loss, right? But we're going to use, for the style loss, we're going to use Van Gogh's irises. And for the content loss, we're going to use the image that we're currently looking at. We've got lots of images we're going to go through. And what we do is we're going to, rather than changing the pixels of the original photo, instead what we're going to do is we're going to train a CNN, or a whole bunch of layers of a CNN. We're going to train a CNN to take this, I think the best way to show you this, let's move this out of the way. Yeah, that's better. So let's put a CNN in the middle. These are the layers of the CNN, right? And we're going to try and get that CNN to spit out a new image. So there's an input image and there's an output image. And this new CNN we've created is going to spit out an output image that when you put it through this loss function, hopefully it's going to give a small number. And if it gives a small number, it means that the content of this photo still looks like the original photo's content, and the style of this new image looks like the style of Van Gogh's irises. So if you think about it, when you have a CNN, you can really pick any loss function you like, right? We've had to use pretty simple loss functions so far, like mean squared error or cross entropy. In this case, we're going to use a very different loss function, which is going to be style plus content loss using the same approach that we used just before. Right? And because that was generated by a neural net, we know it's differentiable. And you can optimize any loss function as long as the loss function is differentiable. So if we now basically take the gradients of this output, not with respect to the input image, but with respect to the CNN weights, and we can take those gradients and use them to update the weights of the CNN, so that the next iteration through, the CNN will be slightly better at turning that image into a picture that has a good style match with Van Gogh's irises. Does that make sense? So at the end of this, we run this through lots of images, we're just training a regular CNN, and the only thing we've done differently is to replace the loss function with the style loss plus content loss that we just used. And so at the end of it, we're going to have a CNN that has learned to take any photo and will spit out that photo in the style of Van Gogh's irises. And so this is a win, because it means now in your web app, which is your Van Gogh irises generator, you now don't have to run an optimization path on the new photo, you just do a single forward pass to a CNN, which is instant. Yes, green box over there.
So this is going to limit.
Does anybody want to talk about
well,
this
so
before
does-
we hear the questions?
Does this mean you take the, you do training to be able to feed in a style on an image, and you hard code, so you do that once, you generate this thing that will, like we did last time, and now you take what you did in that and you use it to train a CNN, or are we training that box on the right as well as the CNN this time?
This is from my understanding, this is a whole different process than the one before. Where before we were just tuning these weights, that were input weights, and now we're tuning CNN layer weights. And so we're hoping that this is going to be a more general approach to styling Van Gogh. Does anybody else want to try to reword that? It makes sense in my head, but it's
Okay, so we're not actually doing any training of that cube on the right-hand side.
that's just the
Those-
loss function.
the-
We
Those
weren't
weights,
training-
the weights in there were
Oh.
from VGG or whatever, and those are fixed. Those are frozen.
Okay.
Yeah,
Right,
the
those
CNN
are
weights
the
are
five
more-
different levels, okay, I get it. Okay, sorry, carry on.
we can. I think it would be. This is a good stopping point to talk about. This is a really, I've never seen this before. This is, really
Is
cool.
this all, this is a prelude to the super resolution thing, right? I mean, it's just,
Super.
Well, you've seen this before.
yeah,
But you
lost
only
the plot a little bit, but, okay. I'm wondering if he's gonna do a UNet type thing to get the greater spatial.
But I don't think you need to bottleneck like
Yeah,
a
there's no
UNet
bottlenecking.
or an autoencoder. I think you can just do straight convolutions.
I don't know what you mean by bottleneck, but I'm thinking in order to capture a style that's more than 3 pixels by 3 pixels, that you might kind of need to zoom out a bit somehow.
Well, you accomplish that by picking a bunch of different layers for the style and training that loss. I think that kind of, each of those different layers is a different resolution or a different kind of field of view onto the image.
But like if you have 2 3 by 3 layers, now the receptive field is actually 5 by 5 of the second one.
That sort of
concept?
thing, yeah. Because it's like, yeah, we're taking like the first 5 layers, and each of those outputs is treated as a loss with respect to the style image.
Okay.
I remember one point I was coming up here, so I can double check what he was talking about, just taking the last or like the 5th layer to help maintain what that picture is, so like of the bird, in order for it to actually look like a bird again afterwards when they apply the style, that they're just taking one of the last layers. But he's going to talk about it coming up.
Oh, okay. Okay. Andrew, if you've made it this far, can you put a cat emoji into the Slack channel?
You know, next week we're gonna get Andrew posting all these things.
I hope so.
Significance of you, like let's say you're Photoshop and you want to change multiple styles.
Yeah, this is going to each neural network is going to learn to do just one type of style.
Is there a way of like combining multiple styles, or is it just going to be a combination of all?
You can combine multiple styles by just like having multiple bits of style loss and multiple images, but you're still going to have the problem that that network has only learned to create one kind of image. Right? It hasn't learned. Now, it may be possible to train it so that it takes both a style image and a content image, but I don't think I've seen that done yet, as far as I know. Right?
Pause. Has anyone done that yet? Has anyone seen anybody doing that?
Can you reword what it is?
Instead of taking an image as your input, you take two inputs, one style, one content.
I'm a bit confused. It looked like that's what he was doing with a bunch of these other things. Like with the bird, you have one, here's the content, here's my original, like later bird or whatever it is, or the other case, the bridge. Here's a style. And he's blending them to make the two.
He's
So
doing
I'm not understanding what he's saying, I guess.
top method.
Steps.
That requires iteration.
Yeah.
So now we're trying to figure out how to do that in a single pass.
Just one pass.
So
Yes, okay. Yeah.
It's if you just blend those together, you will just receive some image and you wouldn't know what to do with it, because you wouldn't know like what part of that mixed image belongs to the style and what part belongs to the image. You know, if you will just do like, I don't know, some of the pixels or whatever. So you have to have those separately so that network knows what is supposed to be the shape and what is supposed to be the style. In that original version.
Okay, yeah, that makes more sense.
It's a great question.
Thanks.
Having said that, there is something simpler and, in my opinion, more useful we can do, which is rather than doing style loss plus content loss, let's think of another interesting problem to solve, which is called super resolution. Super resolution is something which, honestly, when Rachel and I started playing around with it a while ago, nobody was that interested in it. But in the last year or so, it's become really fun.
What did he say?
Remember, Bruce.
What?
we're
Super resolution.
he got bored with style transfer. We're doing super resolution now.
Yeah.
I'm trying to keep up.
And he said
All right,
no one was interested in
I
it.
missed some of the words in it. That I guess it's
He just said he and Rachel were fooling around with super resolution before anybody even cared about
And
it.
Rachel
Didn't
was
used to be
probably the
cool.
words that I
Okay.
missed.
Yeah,
Okay,
yeah.
thank you.
Yeah.
Okay.
Okay, sorry.
That's Rachel.
It was less than a year ago that
Yeah, so we were kind of playing around with it quite a lot. We thought it was really interesting, but suddenly it's got hard. And the basic idea of super resolution is that you start off with a low-res photo. And so the reason I started getting interested in this was I wanted to help my mum take her family photos that were often pretty low quality and blow them up into something that was big and high quality that she could print out. So that's what you do, is you try to take something which starts with a small low-res photo and turns it into a big high-res photo. LR low-res, HR high-res. Now perhaps you can see that we can use a very similar technique for this. What we could do is between the low-res photo and the high-res photo, we could introduce a CNN. Right? And what that CNN could look a lot like the CNN from our last idea, but it's taking in as input a low-res image, and then it's sticking it into a loss function, and the loss function is only going to calculate content loss. And the content loss it will calculate is between the input that's got from the low-res after going through the CNN compared to the activations from the high-res. So in other words, has this CNN successfully created a bigger photo that has the same activations as the high-res photo does? And so if we pick the right layer for the high-res photo, then that ought to mean that we've constructed a new image. What's that, Rachel?
there's a question, can we just stick a CNN between any two things and it will learn the relationship?
Yes, absolutely. And this is one of the things I wanted to talk about today, is, in fact, I think it's at the start of the next paper we're going to look at, is they even going to talk about this. So this is the paper we're going to look at today, Perceptual Losses for Real-Time Style Transfer and Super Resolutions. This is from 2016. So it took like about a year or so to go from the thing we just saw to this next stage. Is that right? Oh, maybe half a year. Okay. So what they point out in the abstract here is that people had done super resolution with CNNs before, but previously the loss function they used was simply the mean squared error between the pixel outputs of the upscaling network and the actual high-res image. And the problem is that it turns out that that tends to create blurry images. And it tends to create blurry images because the CNN has no reason not to create blurry images. And blurry images actually tend to look pretty good in the loss function, because as long as you get the general, oh, this is probably somebody's face, I'll put like a face color here, and it's going to be fine. Whereas if you take the second or third conf block of VGG, then it needs to know that this is an eyeball, or it's not going to look good, right? It needs to know that this is a nose, or it's not going to look good. So if you do it not with pixel loss, but with the content loss we just learned about, you're probably going to get better results. So this, like many papers in deep learning, this paper introduces its own language, and in the language of this paper, perceptual loss is what they call the mean squared errors between the activations of a network with two images. So the thing we've been calling content loss, they call perceptual loss. So one of the nice things they do at the start of this, and I really like when papers do this, is to say, okay, why is this paper important? Well, this paper is important because many problems can be framed as image transformation tasks, where a system receives some input and chucks out some other output. For example, denoising. Learn to take an input image that's full of noise and spit out a beautifully clean image. Super resolution, take an input image which is low res and spit out a high res. Colorization, take an input image which is black and white and spit out something which is color. Now, one of the interesting things here is that all of these examples, you can generate as much input data as you like by taking lots of images which are either from your camera or you download off the internet or from ImageNet, and you can make them lower res. You can add noise. You can make them black and white. Right? So you can generate as much label data as you like. And that's one of the really cool things about this whole topic of generators, virtual to your ledger.
I did have to get something. Well, with that example, so going to lower res imagery camera, it's algorithmically done. So is the neural net only going to learn how to like transport out something that's algorithmically done versus an actual low res imagery that doesn't have like?
Yeah. So one thing I just mentioned is the way you would create your label data is not to do that low res on the camera. You would grab the images that you've already taken and make them low res just by doing filtering, in CV or whatever. And yeah, that is algorithmic, and it may not be perfect, but there's lots of ways of generating that low-res image. You can add, so there's lots of ways of creating a low-res image. So part of it is about how do you do that creation of the low-res image, how well do you match the real low-res data you're going to be getting. But in the end, in this case, things like low-resolution images or black and...
I have a comment. And Ducky's gone, so that's good timing. I missed the meetup last night.
Yeah.
But it was on speech and denoising, denoising speech.
Yep.
Can you apply a similar analogy with this to noisy speech or?
No, because it just won't help you reduce any kind of noise. People have done super resolution for audio. I'm not exactly sure what they're trying to accomplish doing that. I think the more interesting problem that's a little bit like this is if you have gaps in your picture and it'll infill the gaps for you. That's more interesting because you can have gaps in audio. But this, I don't know, the image is degraded with noise. I guess he's saying it could be used that way, this paper is.
You could add noise to like a speech.
You can always just add noise and then do this sort of, train to clean up the noise. The paper last night was using a specific way of doing that, this sort of Bayesian probabilistic model of speech in order to get at the clean speech. So you sort of have this model of what clean speech is. So you feed in noisy speech and it sort of ignores everything that isn't clean speech based on its model, and what you're left with is a cleaned up version. It's other people have done things closer to this though, where basically you just give examples of noisy speech, clean speech, and run it through a network and train the network to fix it up. They tend to be, I don't think they generalize very well, particularly, so that's why these guys in the paper last night were trying to say, let's try to model clean speech, because that should be consistent. Clean speech is always clean speech, but noisy speech can be noisy in a whole bunch of different ways. So rather than training to get rid of specific types of noise, let's train to learn what clean speech is, and then everything that's not clean speech is noise, and we can get rid of that.
The Halloween translation paper that was the second paper I talked about in my blog post. basically added noise. In order to facilitate sentence translation. They had good sentences, and then they messed with the sentences. They broke them, and they had something learned to fix them. Then they did word-by-word translation from French into English, and then had the thing that they'd trained fix the sentences. So that's a very interesting way to train away noise.
So I wonder, he's doing part of this because his mom didn't have as good of a camera. So if we gave her a better camera, would he be more appreciative? But then again, if we gave her a worse camera, we might get really nice models, even better models.
I think we'd also have to go back 50 years.
Yeah, you need a time machine as well. Retake all the pictures with a better camera. I just posted on the Slack channel.
Or you just hack into the computer
Or just hack
now
in.
and lower the resolution.
There's online sites where you just upload images and it'll upscale it by a factor of, at least factor of 4, maybe more, using these super resolution techniques. It's sometimes it's good, sometimes it's not so good. Yeah.
So you can think of super resolution as you've got kind of 3 pixels missing and 1 pixel there, so you're filling in gaps.
Oh yeah, kind of.
I'm wondering if we could fill in more interesting gaps.
Yes, absolutely.
The edges of pictures, or just if you block stuff out.
Yes, there are techniques like that for sure. It's a little different from this. I don't know exactly how that's
could
done.
Imagine what was behind something in a picture if you.
If you. I'm not sure about that.
It makes sense, because if you're using the same thing around the edges, it's simply the edge of whatever is there. So behind me on the wall, what's behind there versus here's the end of the wall. Is there more wall, or is it?
Really, it's possible, but I really like the thing, I don't remember where I read it, that the neural network hallucinates about what's there in those missing points when we do the super resolution. So technically it can hallucinate what's there behind the scene.
Yeah,
it doesn't see. We just don't know how close it will be to reality.
In 10 years, you'll be doing super resolution that will have this smiling family and an axe murder and a knife murder behind them.
Only we'd known. So Photoshop has this content-aware fill thing. A lot of you are probably familiar with that. So you delete something and it fills it in a reasonably convincing way. It often works pretty well. But there are deep learning. It's not deep learning at all. There are deep learning approaches that do the same thing, where they basically benchmark it against Photoshop, and they say they get a lot better results. So.
I want to try to build something like that extrapolates the outer edge of a photo and just run that iteratively and see what it creates. That could have interesting results.
Make a nice frame for the photo if nothing else.
In 2010, some friends of mine and I made predictions about what would happen in the next 10 years. And one of the predictions I made was that 80% of the interior spaces of San Francisco would be mapped by Google. So, what you could have is and I don't know if that's going to happen, but if it did, then you could have the neural net go, okay, where was this picture taken? Okay, I see where it was taken, and there's a wall there.
That would be cool.
That'd be scary.
Maybe for a little bit, but then I think I'd get comfortable with just the computer overlords. Knowing everything.
Trying to upscale.
Yeah, I'm trying to find it. Hey, computer overload, if you can hear us, post something to the Slack channel.
3 years from now, there's the cat photo by computer overlords.
It's just processed all of this, yeah.
Yeah.
Overlords. Matt was only saying that because he thought you were listening, but as soon as he's off camera, you know.
All right, we're good.
White images. It's so hard to start with something just like I've seen versions with just an 8x8 picture and turning it into a photo. It's so hard to do that regardless of how that 8x8 thing was created, that often the details of how the low-res image was created don't really matter too much. There are some other examples they mentioned, which is turning an image into an image, which includes segmentation. we'll learn more about this in coming lessons. But segmentation refers to taking a photo of something and creating a new image that basically has a different color for each object. So horses are green, cars are blue, buildings are red, that kind of thing. So that's called segmentation. As you know from things like the fisheries competition, segmentation can be very important as a part of solving other bigger problems. Another example they mention here is depth estimation. There's lots of important reasons you would want to use depth estimation. For example, maybe you want to create some fancy video effects where you start with a flat photo and you want to create some cool new Apple TV thing that like moves around the photo with a parallax effect, as if it was 3D. So if you were able to use a CNN to figure out how far away every object was automatically, then you could like turn a 2D photo into a 3D image automatically. Taking an image in and sticking an image out is kind of the idea in computer vision, at least, of generative networks or generative models. And so this is why I wanted to talk a lot about generative models during this class. It's not just about artistic style. Artistic style is just my sneaky way of introducing you to the world of generative models. Okay, so let's look at how to create this super resolution idea. And your homework, or part of your homework this week, will be to create the new approach to style transfer. Okay, so I'm going to build the super resolution version, which is a slightly simpler version, and then you're going to try and build on top of that to create the style transfer version. Okay, so make sure you let me know if you're not sure anymore. So I've already created a folder of 20,000, a sample of 20,000 ImageNet images, and I've created two sizes. One is 288 by 288, and one is 72 by 72. And they're available as bcols arrays. Okay, so I actually posted the link to these last week, and it's on platform.fast.ai. So we'll open up those bcols arrays. And one trick you might have hopefully learned in part one is that you can turn a bcols array into a NumPy array by slicing it with everything. Right? So anytime you slice a bcols array, you get back a NumPy array. So if your slice is everything, then this turns it into a NumPy array. This is just a convenient way of sharing NumPy arrays in this case. So we've now got an array of low-resolution images and an array of high-resolution images. So let me start maybe by showing you the final network. Okay, this is the final network. So we start off by taking in a batch of images, low-res images. And the very first thing we do is stick them through a convolutional block with a stride of 1. Okay, so this is not going to change its size at all. But this convolutional block has a filter size of 9.
I thought he was going to be doing a lot of TensorFlow coding, but it's just all Keras so far.
He's going to do any TensorFlow.
Why was I under the impression that it was going to be TensorFlow?
He's saying in the introductory thing to this part that he's going to do TensorFlow and PyTorch as well. But
I mean, but if it's like a custom optimizer or custom loss function, then you could just write some TensorFlow to do that. But then you could just stick it into Keras, right? Which is the nice thing. So you only need to dabble with TensorFlow when you absolutely have to. Maybe that's what he meant.
That's nice.
But I haven't actually watched the video yet, so I don't know.
In industry, do they use Keras much, or do they go more directly to TensorFlow?
Industry?
Yeah.
Probably more TensorFlow because
Directly, yeah.
It depends what they're trying to do, I guess. But
does industry exist yet?
Yeah, is industry doing either? Not so much.
I'm sure plenty of people are using Keras.
Yeah. Depends. If your model's simple enough, sure, use Keras. But if you got into something, you might have to go beyond it.
I mean, how many people are just using sort of like standard ImageNet, where it's not even sort of training? They're just
probably lots.
Using
just
that.
Doing that, yeah. Path of least resistance.
Functional API, by the way.
True. Yes.
You're right.
So let me remind myself. So 64, that's the number of features. 9 is, what's
filters?
Filter size. It's pretty big.
Oh, it's just the filter size. Okay, yeah. So it's 9 by 9.
9's big, right?
And the 1 is the stride.
Yeah.
Like the idea.
Yeah.
Okay.
Yeah.
I was mixing up my stride.
Filters, size.
Oh, there it is, right there. Got it.
Mode, same. Act, true. Well, I don't know what
Where
that
does
is.
that act come in?
Doesn't
Oh,
have-
activation.
Oh, got it, yeah.
Oh, if act, else.
If there's
Okay.
an activation,
Yeah.
else you just spit it out.
I don't like his variable names.
Else X. Oh, I see. Right.
Yeah.
Those extra letters really,
Yeah.
matter.
Well, once upon a time, those extra letters were important, when your screen size was 40 characters wide. .80, but
And variables were all five characters.
hey, my mom in like 1970 wrote a program where she had 56 variables named V1, V2, V3, V4 up to V56, and they were 8-bit variables, and she needed like 69 6-bit variables. So she packed and unpacked every one of those damn variables when she needed them with names like V1, V2, etc. Anyway, sorry.
You're
My
gonna
mom
get
has an email
It's
address
just-
now.
Giving you the final network. Okay, this is the final network. So we start off by taking in a batch of images, low-res images. And the very first thing we do is stick them through a convolutional block with a stride of 1. Okay, so this is not going to change its size at all. But this convolutional block has a filter size of 9, and it generates 64 filters. So this is a very large filter size. Particularly nowadays, filter sizes tend to be 3. Actually, in a lot of modern networks, the very first layer is very often a large filter size. Just one very first layer. And the reason is that it basically allows us to immediately increase the receptive field of all of the layers from now on. Right? So by having 9 by 9, and we don't lose any information because we've gone from 3 channels to 64 filters. Right? So each of these 9 by 9 convolutions can actually have quite a lot of information because you've got 64 filters. So you'll be...
So wait, what?
Is that true? I thought that people had switched over to just doing 3 by 3 on everything.
Yeah, that's what I thought too.
No,
But when
ResNet
did
starts off with a 7 by 7.
Do they?
Yeah. Seems like a massive amount of entropy to fight against though to train them. So yeah,
So 64 is the number of filters, not 9?
That is the filters. 9 is like, it's a 9 by 9 kernel that you're training.
Oh,
So,
And then how many different 9 by 9 kernels?
Okay.
64 of them.
Okay,
So-
that's a lot.
So usually you have way more channels than 3. So it's also a time when you can take advantage of. You start with only 3 channels. So computationally it's
Why would you
not
have
that
more than 3
expensive.
normally?
like
But
we're
it's
at the
still
input
a-
layer here, right? You just got RGB channels.
Exactly.
on
So you
input.
only, exactly. You only have 3 coming in. So you're not
Okay.
gonna. So that means if you've got 3 channels going to 64, you're gonna have way fewer weights than
Oh,
if
you
you
mean
have
in-
64 going to 64.
Yes.
In the
So-
later layers, you mean?
Yeah.
So-
Just the amount of filters that you're creating.
Yeah.
Mhm.
So if you
Kernels.
did a 9 by 9 from the first layer to the second layer instead of from the picture to the first, it'd be
Right.
computationally way more expensive.
Yes, that is accurate. But
So now's the
I
time.
still
to,
don't like it.
Yeah.
If now's the time to do it, why don't you go even more than 64, like 128 or?
Yeah, why 9? Why not 15? Why
I
not
don't know why.
127?
You must hit a limit.
I thought you usually went like you'd go in brackets 3, to say it's a 3 by 3.
Yeah, he does this is
This
his
is
own
short
function that he
hand.
wrote.
Oh, okay.
He's always assuming you're gonna have a square thing,
Right,
so he just
okay.
wants one number.
I think Keras will, you're gonna have to give it a single integer or a list, or a tuple. Yeah. So, most people use square, well, not usually, so they have that convenience.
I think
Are
you
you
could
just-
you could like computationally, if you did 12 by 12 or something like that, it would be okay. You won't start making your whole network way more expensive.
But how like it's gonna be so difficult to find edges in a 12. Like how many different sorts of edges can you find in a 12 by 12 thing? Like he's only allowing 64 per color channel. Only 64 combinations of weights. It's like you're gonna be you're gonna be finding edges inside edges. Like it's gonna be overfitting. It's not gonna be. I really don't think it's gonna be generalizable very well. That's.
Yeah, no, that's
Well, but wait a
there
minute.
does seem to be like a. You want it to be large enough, but then the more you increase it, the more you're going to suffer from this problem. That like so obviously like the extreme limit is like a filter thing size the entire image, and you're just trying to like find your filters that are essentially different images. They're just trying to see more or less like that, and that's obviously extreme because you're essentially fitting the filter to each image. But then if you're sort of doing like a quarter of the image, then it'd be like you're just fitting to a part of it.
Yeah.
So at some point, that it's going to give way to like a 3x3 where you're just getting some very basic edge detections and sort of things like that. So there's something in the middle, but where that middle is very not obvious.
Intuitively, I feel that also having only one size is not a good idea, because like certain things that we spot are based on the long, like when we do our vision, based on the long lines. Something when we spot it's based on the small bright object, and so like we have various sizes of filters inside of our brain. Some spot small objects, some spot bigger objects. So I feel that probably like if I would be implementing this visual like picture analyzer, whatever, I would try to have a different kernel sizes for different filters, like finding different features.
But even if you pile up all 3x3 filters, you can get layers that recognize larger images that will go off, right? So you can still get that effect of noticing different things, small and large.
But how will you see that there is a like line that goes through the full image if you will have only a 3x3 convolutional?
Because the layers down have a bigger receptive field, and so if there's a line that goes down, well then that's going to show up because that line picking up thing is going to activate in all of these. It's just going to activate in a line, I guess.
We could do this as an experiment. I care it's pretty straightforward. So just create a network which instead of just as like 3x3, you just chuck in like similar conv block. And then you just sort of append them all together and just shove them into a dense layer or something. Yeah, you can concatenate them as an experiment to see how. I mean,
as long as
you need the depth in there.
Yeah, as long as you do something on top of those features, like you still have the map, or yeah, I was wrong.
I quite liked in your talk, Bruce, the part where Julia was explaining how they have some convolutions that skip, so it's like 3x3, but it has a receptive field of
dilated convolutions.
Convolutions, yeah. But it was only ever used inside of one layer. It wasn't used in like a normal convolutional step or where you're max pooling after that. I don't think.
Well, in this case, maybe not max pooling. No, not the max pooling part. That's true. But you can stack up those. Use that to replace your convolutional layer and then stack them up. There's several of them.
All right.
Seeing this quite a lot in modern CNN architectures, just a single large filter conv layer. So this won't be unusual in the future. Now the next thing, can I get the green box behind you? Oh, just a moment, sorry. Yeah.
The stride one also pretty popular these days?
Yeah, well the stride one is important for this first layer because you don't want to throw away any information yet, right? So the very first layer, we want to keep the full image size. So the stride one, it doesn't change, it doesn't downsample at all.
But there's also a lot of duplication, right? Like 9 filter size and 1.
Yeah, they overlap a lot, absolutely. But that's okay. A good implementation of a convolution is going to hopefully minimize some of that, or at least keep it in cache, so it hopefully won't slow it down too much. One of the discussions I was just having during the break was like, how practical, are the things that we're learning at the moment compared to like part one, where everything was just designed entirely to be like, here are those practical things which we have best practices for. And the answer is like a lot of the stuff we're going to be learning, no one quite knows how practical it is because a lot of it's just hasn't really been around that long, and it's really that well understood, and maybe there aren't great libraries for it yet. So one of the things I'm actually hoping from this part two is by learning the edge of research stuff or beyond amongst a diverse group, is that some of you will look at it and think about whatever you do 9 to 5 or 8 to 6 or whatever, and think, oh, I wonder if I could use that for this. If that ever pops into your head, please tell us, right? Please talk about it on the forum, because that's what we're most interested in. It's like, oh, you could use super resolution for blah, or depth finding for this, or generative models in general for this thing, I do in pathology or architecture or satellite engineering or whatever. So it's going to require some imagination sometimes on your part. And so often that's why I do want to spend some time looking at stuff like this, where it's like, okay, what are the kinds of things that this could be done for? But one of the, I'm sure in your own field, like one of the differences between an expert and beginner is the way an expert can look at something from first principles and say, okay, I could use that for this totally different thing, which has got nothing to do with the example that was originally given to me, because I know that the basic steps are the same, right? And that's what I'm hoping you guys will be able to do, is kind of not just say,
Is this right? Better to go?
I just had an idea. Maybe you can train so that you can take a 2D image and you can look at it as though it's 3D. Or maybe
I
if
mentioned
you-
that, I think.
Yeah. That's,
So you get virtual reality, yeah.
Yeah.
Yeah, it's sort of like the same object but at different
Depth.
angles maybe, or
depth estimation.
well, where your data would, what data you need to in order to do that.
Well, he's talking about depth and parallax, but not as much as you look at the front and then you're able to suddenly like rotate around and look at the back.
The back.
Yeah.
Looking at the back, I think I might have troubles doing this, but if you could,
Yeah.
10 degrees either side. So
Well,
yeah, I think it might be able to
well, if you
do that kind of thing.
yeah.
if you get to recognizing objects, particularly people, if you look at somebody's front, you kind of know what their back is going to look like.
Yeah.
Much harder to do their faces to figure out from the
Yeah,
back.
that would be really impressive.
Well, for the Carvana data set,
Yeah.
you had like a load of the same cars but had taken at different angles, right?
Yes.
So it seemed like that would be a good data set to try this on.
Yeah.
It would. Mm-hmm.
There'd be a use case in virtual reality.
Yeah.
You could just take photos and you could go explore the area.
Yeah.
That's cool.
I'm sure if you could start with 2 photos, like, it could do a much better job.
I'm sure.
Then it could tell the depth.
Well, it still wouldn't be able to tell the back.
Yeah.
No.
But if you're making a company, you want one photo. You don't want people to have to take 2 photos of something.
Yeah, you're right.
Or video, because people can make video, and video is essentially is multiple photos.
Mm-hmm.
Yeah, if I'm selling my car, and then I can just take one picture of it, and then someone can zoom and drag to move the car around.
Well, I take a picture of the side that doesn't have the dent.
Fill in the gaps.
The other side must look exactly the same, yeah. So the data is being informed by used car photos, so it might not be the case. It might introduce dents that aren't there.
Yeah, so basically we now have a startup. You know, when they sell like property, they usually try to make shiny photos of everything. So basically we might have a tool for them where they just make a photo of the usual apartments and as a result they see how shiny it might be.
There is this thing about estate agents taking terrible photos of the properties they're trying to sell.
Some of them,
So
I've
you
been
got
looking at stuff.
quite a
Some
few blogs of
so
just
bad.
incredibly depressing. It's probably a nice place, but just like they've just managed to take the worst photo.
Uh-huh.
So a way of somehow taking a bad photo like that and then using this transformation to turn it, get it from the right perspective or the right angle, or just adjust the lighting a bit to make it.
I
Photoshinification.
think this is the
Yeah.
best example of that I've seen. Beautiful looking car, great. Oh.
What?
It's a car for sale I was looking at. So really nice BMW 2002.
Yeah.
You're saying those
Yeah,
are the same car?
Bondo.
Yeah, it's an ICBC wreck. But it looks so nice from that
Yeah,
angle.
from that side, yeah.
Yeah.
And Andrew's just gonna have to imagine what it looked like.
Yeah.
If like 2 of them glued together.
Little Bondo.
Bruce, do you remember a guy who used to come to the meetup a long time ago? Pei? Gia
Yeah.
Pei?
Mhm.
Is that his first name? Gia?
Yeah, Pagea.
He worked at a company that was like modeling or it was like taking a lot of photos of the inside of a house so that you could walk through it.
Yeah,
as
that's
it-
right.
Yeah,
Yeah. So VR tour of the house. Yeah.
yeah. That's a great idea.
And Alexi actually works for a company that figures out how much it's going to cost to repair those dents.
Oh.
Huh.
Cool.
Yeah, I remember talking about that. Yeah.
I remember having a debate with somebody about that. About how reasonable it was to do that with deep learning. Maybe it was Alexi.
Well, I think
Well, I hope you had the right opinion. You'd be a fool to go after something like that. Yeah.
one of the first days. One of the
I think
first
it's possible, probably. Sorry.
first days I met him at dinner afterwards, he was talking about the troubles he was having buying dented hoods. He needed to buy dented hoods because he needed to take.
Life is hard.
photos
First
of
world
themselves.
problems.
Yeah.
Yeah.
Did Bruce say who's gonna fill the mushroom?
Oh, he's getting a drink.
Getting water.
This one, yeah.
Speaking about drinks,
Yeah, you wanna
when we are gonna finish today?
In 16 minutes.
Yeah, actually in like 12 minutes, depending on how fast.
No, but I will end it
Yeah.
at 8:30 or at 9.
Can we leave the door open?
I think we go until we finish
Yeah,
halfway,
it's
and
good.
that'll be
Yeah.
around 8:30.
That's good.
8:35.
I don't think we will finish the half by 8:30.
Oh, we can do it.
Hold my beer. It's a method.
Yeah, it's not to say, okay, now I know how to do artistic style. Are there things in your field which have some similarities to artistic style? So we were going to talk about the super resolution network. And we talked about the idea of the initial conf block. So after the initial conf block, we have the computation. And when I say the computation, in any kind of generative network, there's like the key work it has to do, which in this case is starting with a low-res image, figure out like, what might that black dot be? Is it an eyeball, or is it a wheel? Basically, if you want to do really good upscaling, you actually have to figure out what the objects are so that you know what to draw, right? So that's kind of like the key computation this CNN is going to have to learn to do. In generative models, we generally like to do that computation at a low resolution. And there's a couple of reasons why. The first is that at a low resolution, there's less work to do, so the computation is faster. But more importantly, at higher resolutions, it generally means we have a smaller receptive field. It generally means we have less ability to kind of capture large amounts of the image at once. And if you want to do really great kind of computations where you recognize that, this block here is a face, and therefore the dot inside it is an eyeball, then you're going to need enough of a receptive field to cover that whole area. Right? Now, I noticed a couple of you asked for information about receptive fields on the forum thread. So there's quite a lot of information about this online, so Google is your friend here. But the basic idea is, if you have a single convolutional filter of 3x3, the receptive field is 3x3. So it's how much space can that convolutional filter impact. Okay, so here's our 3x3 filter. Now, on the other hand, what if you had a 3x3 filter which had a 3x3 filter as its input, right? So that means that the center one took all of this, right? But what did this one take? Well, this one would have taken, depending on the stride, probably these ones here, right? And this one over here would have taken these ones here. So in other words, in the second layer, assuming a stride of 1, the receptive field is now 5 by 5, not 3 by 3. Right? So the receptive field depends on two things. One is how many layers deep are you? And the second is how much did the previous layers either have a non-unit stride, or maybe they had max pooling. Right? So in some way they were coming down sample. And those two things increase the receptive field. And so the reason it's great to be doing layer computations on a large receptive field is that it then allows you to look at the big picture, look at the context. It's not just edges anymore, but eyeballs and noses. So in this case, we have 4 blocks of computation, where each block is a ResNet block. So for those of you that don't recall how ResNet works, it would be a good idea to go back to part 1 and review. But to remind ourselves, let's look at the code. Here's a ResNet block. So all a ResNet block does is it takes some input, and it does 2 convolutional blocks on that input, and then it adds the result of those convolutions back to the original input. So you might remember from part 1, we actually kind of drew it. We said there's some input, and it goes through 2 convolutional blocks, and then it goes back and is added to the original. Right? And if you remember, we basically said in that case, we've got y equals x plus some function of x, right? Which means that the function equals y minus x, and this thing here is a residual. Right? So a whole stack of residual blocks, ResNet blocks, on top of each other can learn to gradually hone in on whatever it's trying to do. In this case, what it's trying to do is get the information it's going to need to upscale this in a smart way. So we're going to be using a lot more of this idea of kind of taking blocks that we know work well for something and just reusing them. Right? And so then what's a conv block? Well, all a conv block is in this case is it's a convolution followed by a batch norm, optionally followed by an activation. And one of the things we now know about ResNet blocks is that we generally don't want an activation at the end. And that's one of the things that the more recent paper discovered. So you can see that for my second conv block, I have no activation. I'm sure you've noticed throughout this course that I refactor my network architectures a lot. Right? My network architectures don't generally list every single layer, but they're generally functions which have a bunch of functions which have a bunch of layers. A lot of people don't do this. Like a lot of the architectures you find online are like hundreds of lines of layer definitions. I think that's crazy. It's so easy to make mistakes when you do it that way, and so hard to really see what's going on. So, in general, I would strongly recommend that you try to refactor your architectures so that by the time you write the final thing, it's half a page. And you'll see plenty of examples of that, so hopefully that'll be helpful. All right, so we've increased the receptive field, we've done a bunch of computation, but we still haven't actually changed the size of the image, which is not very helpful. So the next thing we do is we're going to change the size of the image. And the first thing we're going to learn is to do that with something that goes by many names. One is deconvolution, another is...
I'm going to slow this down.
So this is the thing that he should be calling transpose convolution. And in fact, it looks like he's calling a Keras function called deconvolution, but I'm sure they've changed the name now to transpose convolution. So if you're trying to do something with the new Keras, his code won't work.
Is this... No, he did update to Keras 2, though. Pretty sure.
Did he for this course? Not so sure.
Just neural style? Is that the notebook he's working on?
Probably, maybe. Or maybe one after that.
Let's see.
Oh my god!
What are you doing? Wow, it guessed it right.
I used to just be more...
Could have typed in anything there.
The power of deep learning.
Yeah.
Super resolution,
You see conv 2D transpose, that's the thing. Now there is an upsampling. I'm not quite sure what upsampling does.
When did Keras 2 come out?
I think it's after this course, wasn't it? Like, because this course is like February or something. I thought the Keras 2 was...
Maybe it came out in the middle of this class, yeah.
Yeah.
March
That's not-
16th.
March
So a month
16th.
after he filmed it.
All right.
So, low likelihood of Keras 2 being...
Yeah. In fact, I know for sure because I tried to run the notebook and I have Keras 2 installed and it was crapping.
There you go, yeah.
Yeah, transpose, yeah. But because you all went to the Kaggle meetup a little while ago, you know all about that now.
That's right.
Deconvolution 2D. Yeah.
It's also known as transposed convolutions.
Whoa! Out of nowhere.
And it's also known as fractionally strided
Wow.
convolutions.
Yeah.
In Keras, they call them deconvolutions. And the basic idea is something which I've actually got a spreadsheet to show you. Okay, so here's a spreadsheet. The basic idea is that you've got some kind of image. So here's a 4x4 image, some 4x4 data, right? And you put it through a 3x3 filter, convolutional filter. And if you're doing valid convolutions, then that's going to leave you with a 2x2 output. Because here's one 3x3, another 3x3, 3x4. And so each one is grabbing the whole filter and the appropriate part of the data. Right, so it's just a standard 2D convolution. Right, so we've done that. Now let's say we want to undo that, right? We want something which can take this result and recreate this input. Right? How would you do that? So one way to do that would be to take this result.
Everybody uses this example, starting with the Theano, so everyone copies the Theano example. It is just so misleading. The fact that you've got a smaller output here than the input is strictly because of the boundary effects, right? It's kind of irrelevant for the whole discussion, but this becomes the focus of why you do it. It's just so wrong. I don't know why everyone persists in using this example. It took me like a day to unlearn this. To learn what these transpose convolutions are really about, but anyway.
Well, what is true in this? Is there anything that we can take away from it?
Well, I suppose at some point he's going to take a transpose of something. So, okay, if he does that, then, maybe. Except I'm not sure he's going to. I think he'll probably at least reproduce the way people actually calculate these transpose convolutions, which is not as a giant, matrix multiply, but instead as you have this kernel and you add things up as you move it around. So maybe that's going to be true. We'll see.
right? So let's copy it over here, right? And put back that implicit padding. So let's surround it with all these zeros, such that now if we use, let's have some filter, we'll just start at 0, right? We have some convolutional filter, right? And we're going to put it through this entire matrix, a bunch of zeros with our result matrix in the middle, right? And then we can calculate our result in exactly the same way, just a normal convolutional filter. So if we now use gradient descent, we can look and see, okay, what is the error, right? So how much does this pixel differ from this pixel, right? And how much does this pixel differ from this pixel? And then we add them all together to get our mean squared error. So we can now use gradient descent, which hopefully you remember from part 1 in Excel, it's called solver. And we can say, okay, set this cell to a minimum by changing these cells, right? So this is basically like the simplest possible optimization. Solve that. And here's what it's come up with. Right, so it's come up with a convolutional filter. You'll see that the result is not exactly the same as the original data. And of course, how could it be? Right? We don't have enough information. We only have 4 things to try and regenerate 16 things. But it's not terrible, right? And in general, this is the challenge with upscaling, right? When you've got something that's blurred and downsampled, you've thrown away information. That's okay?
Paul, so I think this is quite wrong because his deconvolutional filter, he's applying it as a convolution, which is not correct at all. So a transpose convolution is not a convolution. It's the transpose of a convolution.
Yeah, and to think about how you would generalize the way that he's introduced this to a larger scale image that you're trying to create, which like what you have this tiny thing and you have all these zeros on the outside, and like
Yeah, you're not going to do that, right? Yeah, like you can fill in a couple of zeros at the edges, but yeah, you're not gonna add a million zeros to your image and then try to reproduce it from a couple of things in the middle.
Because he creates an image that's larger than the image that he wants to create. That's right.
Yeah.
But for the true transpose convolutions, do you need the true values of what it was before? Like, do you need to store those in memory as you're going down?
No. So, I mean, typically you'll learn the weights just like you would learn the convolutional kernel weights. It's just the way you apply those weights is different from a convolution.
But what is the ground truth? Like when you're applying the transpose convolution, you're going to create a larger image. Do you measure a loss function with respect to each?
I mean, it depends on the application, but sure, yeah. If you have, I mean, in his case, if you're going to do super resolution, you'll have the high resolution image eventually. So you're going to be comparing the output of this deconvolution thing to the high res image.
Okay, so you'll have the values at the end of the pipeline, and those are the only values you need, and the error is kind of propagated all the way down through that.
Yeah, and that'll train both your convolutional layers and your transpose convolutional layers.
Any way you can get information back is to guess what was there. But the important thing is that by using a convolution like this, we can learn those filters. So we can learn how to upsample it in a way that gives us the loss that we want. So this is what a deconvolution is. It's just a convolution on a padded input. Okay? Now, in this case, I've assumed that my
the first thing I've seen
had
is
a
just like flat out wrong.
That's why they don't call them deconvolutions.
Yeah, it's not that. I really think he's just completely wrong about this.
Can you even double the image size doing it that way?
Not the way he's describing it.
No,
you can only add zeros. You'd never get there.
You can only add a border.
Yeah.
So, yeah, even his network doesn't work.
Right.
With
right. It only works in Excel for his
for this
toy example, this very specific example. Yeah.
But who is the fault of this? Is it the Theano?
It's
people?
Theano stuff. They have this very clear, beautiful
no wonder they
thing
went out of
about
business.
convolution, and then now this transpose convolution. But unfortunately, they illustrate transpose convolution with this example, which is like completely irrelevant. Yeah.
Apparently, Matt Zeiler is to blame for why they call it deconvolutional networks. This goes back to Café, because Café called it deconvolution, and that was based on this person's publication.
Okay.
But apparently, they didn't even call it. He himself, even though he called it like a deconvolutional network, referred to the operation as a projection operator, not a deconvolution operator, but he called the whole network a deconvolution network, and the name stuck.
This is why you gotta pick good names for your.
Yeah.
So it's Matt's fault.
Matt Zeiler.
Yeah, alright.
Would you say it's Matt's fault?
Well, there's so many Matts in this industry.
That's why it's important to pick good names.
Notice we've never been got 3 Matts in this meeting. It's always 2 out of the 3. It's kind of suspicious, right?
Was Emery here last time?
Yeah, for one of them, wasn't he?
No, he hasn't
Oh,
made
has he
it
never
yet.
Emery
been?
has
He
not.
hasn't made it
He's
yet.
Oh,
been
okay.
pretty busy, I
okay.
guess.
He almost came tonight, but anyway.
I think he was
He almost
on the
came
first
the other
one.
2 nights. too.
Nah, he almost came to the other nights too.
I think he was on the first
Then he
one.
remembered he has a job.
Yeah, that's right. That was his excuse.
Oh, you're right, he was here.
He
the
was
first
on the
one,
first,
That's
yeah.
where I gave him the t-shirt.
Yeah.
Yeah, you're right.
I got.
You think
He
you
has
a
a
t-shirt?
Too many Matts.
No, that's right. You got the T-shirt.
Oh, I
yeah.
gave him one t-shirt at a meetup. That's right, I gave it to him.
Does he have one of those T-shirts? Awesome. We gotta.
You got a Matt Brotherhood.
Do you want to get the
What's the
halfway?
t-shirt that you got?
You're not Matt. Sorry.
It's,
You're like the rest of us.
I think I posted a image of it to the channel saying, this is completely off topic, but I did this and I like it. It was a t-shirt I designed for the Unicode conference, and it's kind of it's sort of like a starburst. It's got like 12-fold rotational symmetry, and on the outside there's Sumerian, and then Egyptian, and then Chinese, Korean, Canadian syllabics, the Euro symbol, and then at the very center, an emoji. And
That looks cool. I'm gonna wear it. And
I-
we'll see it at some point.
I got, as part of my compensation for designing the t-shirt, I got all the ones that were left over, and they're all extra larges. And I don't know that many extra large people, so Matt got one, and the other Matt got one because they're extra larges.
So I actually have a comment related to the receptive field. We're talking about 2 3x3 layers on top gives you a 5x5 receptive field, right? One of the things I've been concerned about with dropout and convolutions is that it'll just learn to pass the important features, spread the important features out, so that if in case something drops out, it'll. You know what I mean?
That's the point. That's a good thing, right? What is the concern?
Well, you're losing spatial resolution to preserve that feature exists.
Sorry, you're talking about dropout or
And
max
you're-
pooling?
So with dropout. Yeah.
Dropout.
Losing spatial
Well, you typically only drop out the very end of the network. You don't drop out as you're creating these features.
You normally don't drop at the convolutional layers, right?
DenseNet would disagree with you.
So what he says
I want
is
to hear
that
more on
And
this.
so in
he's
VGG,
dropping out
which is
every layer.
in part 1, they do VGG all the time. They only drop out in the head of VGG after the convolutional layers. But he also said that in modern networks, usually you drop out in the convolutional layers as well. You have lower dropout.
It's smaller though, right? It tends to be like the dropout's big at the top and then gets smaller the further.
You would never
Yeah.
drop out at the very top of the, like, from the input, would you? I'm waiting to hear from Matt on this.
Yeah, I think you don't drop out the first convolution block, but you do in the rest of them in DenseNet.
And does the dropout scale as you go further through?
I don't think
Because
so.
I remember hearing.
Because you just got this.
Oh, you just got a single rate. Yeah.
I was right.
How fast can I go?
Put it to 3!
We got
Yeah,
3
it's
minutes.
Oh, yeah.
Yeah, sorry.
Yeah, it's just at the end of every dense layer.
Oh, then you have like
end of that.
okay, but so even then you're not actually putting it through in the convolutions. It's just like end of every dense layer, then you have some dropout.
Yep.
Yeah.
And the dense layers are like once you have your features that you kind of want to be using.
It's almost like at the end of every ResNet block, you have a dropout that defaults to 20%, I think.
Okay.
20%?
Yeah.
In
DenseNet.
DenseNet. Oh, DenseNet.
Yeah.
I've never heard of DenseNet before.
I think he's going to talk about it in this course
I
at some
like
point.
it. Yeah.
All right, let's get to halfway. We're almost there.
It seems huge.
I think it's fairly standard, isn't it?
That's right.
Is it
Right,
really?
'cause-
Yeah, 20%. I mean, you get up to 50%
Huh.
at the end of VGG.
Huh.
Yeah, VGG's 50%. If
Maybe
you
hammer
dense
it.
Huh.
layer.
I guess I just never looked at the number. Or forgot.
It's to combat overfitting, right?
Yeah, you've got a lot of parameters.
Yeah.
It's just one pixel between each convolution. If your convolutions are of stripe 2, then it looks like this picture. Okay? And so you can see that as well as putting the 2 pixels around the outside, we've also put a 0 pixel in the middle. Okay? So these 4 cells is now our data cells, and you can then see it calculating the convolution through here. I strongly suggest looking at this link, which is where this picture comes from.
Huh.
And in turn, this link comes from a fantastic paper called the Convolution Arithmetic Guide, which is a really great paper. And so if you want to know more about both convolutions and deconvolutions, you can look at this page, and it's got lots of beautiful animations, including animations on, they call it transposed convolutions.
Pause.
So you can see.
So don't look at that paper.
No?
Instead, go to the CS231N course. They've got and just search for transposed convolution CS231N. They have a really good description. That's
Oh, did they?
actually
Yeah,
correct.
those guys are great.
Yeah.
Okay.
Where's that from? 31N?
CS231N, that's the name of a Stanford course.
Okay.
CNN's. It's
Cool.
online.
Really good
has-
class.
It's some of the best explanation of everything. Carpathian, Justin Johnson.
Did Karpathy teach it this last year?
No,
'Cause he's now at
he's moved on. He's at Tesla now.
Tesla.
Yeah, but Justin Johnson's still teaching it, so I guess he's still there. There's some other people.
There we go. This is the one I just showed you, right? So that's the one we just saw in Excel. So that's a good, really great site. Okay, so that's what we're going to do first. Is we're going to do deconvolutions. So in Keras, a deconvolution is exactly the same as convolution, except with DE on the front. Got all the same stuff. How many filters do you want? What's the size of your filter? What's your stride, or subsample, as they call it? Border mode, so forth.
We have a question. If TensorFlow is the back end, shouldn't the batch normalization axis equals -1?
What?
Oh.
And then there's a link to a GitHub conversation where Francois said that for Theano, axis is 1.
Yeah. No, it should be. And in fact, axis -1 is the default. So, yes, thank you. Well spotted.
Thank David Gutman.
Thank you, David Gutman. He is also responsible for some of our beautiful pictures we saw earlier, so double thank you, David Gutman.
Is he going to change it or what?
No.
Let's remove axis.
Oh. That would make me
Okay, that would make
clear.
things
It's
look
gonna
a
be
bit better.
obscure.
And
How
go
did
faster.
he load up the code to the definition? He was hovering his mouse over it, and then it code came, like the definition, the default definition of the function came up. Did anybody know with Jupyter?
Yeah.
It's a
there
Jupyter
was something-
functionality.
There was something he talked
So,
about, I think.
so it
in
just
the
shows
first
all the
lesson.
things that you can enter?
Look, I'm gonna go back.
Just shows the original code.
There's a hotkey for it. Shift
This.
tab.
Oh yeah, Shift Tab. Yeah.
Shift tab will
For
do
that,
it, I
yeah.
think.
Oh.
Yeah.
Fancy.
Wow, that's cool.
Yeah, I only learned that fairly recently. It's pretty good. It doesn't seem to work on all libraries. I guess they have to be documented in a certain way, but it generally works.
It doesn't work while the kernel's busy. It sucks.
Oh, really?
Oh.
Mm.
Yeah.
All right.
That will make things look a bit better and go faster as well. So just in case you were clear on that, you might remember from part 1 that the reason we had that axis equals 1 is because in Theano that was the channel axis, right? So we basically wanted not to throw away the XY information but batch normal across channels. In Theano, channel is now the last axis, and since -1 is the default, we actually don't need that. Okay, so that's our deconvolution blocks, and so we're using a stride of 2,2, right? So that means that each time we go through this deconvolution, it's going to be doubling the size of the image. For some reason I don't fully understand and haven't really looked into, in Keras you actually have to tell it the shape of the output, So you can see here, you can actually see it's gone from 72 by 72 to 144 by 144 to 288 by 288. Right? So because these are convolutional filters, it's learning to upscale. Right? But it's not upscaling with just 3 channels, it's upscaling with 64 filters. So that's how come it's able to do more sophisticated stuff. And then finally, we're kind of reversing things here. We have another 9 by 9 convolution in order to get back our 3 channels. So the idea is we previously had something with 64 channels, and so we now want to turn it into something with just 3 channels, 3 colors, and to do that we want to use quite a bit of context. So we have a 9 by 9, single 9 by 9 filter at the end to get our 3 channels out. So at the end, we have a 288 by 288 by 3 tensor. In other words, an image. So if we go ahead now and train this, then it's going to do basically what we want, but the thing we're going to have to do is to create our loss function. Right? And creating our loss function is a little bit messy, but I'll take you through it slowly and hopefully it will make sense. So we've taken, let's remember some of the symbols here. Input, imp, is the original low resolution input tensor. And then the output of this is called outp, output. And so let's call this whole network here, let's call it the upsampling network. Right? So this is the thing that's actually responsible for doing the upsampling. So we're going to take the upsampling network and we're going to attach it to VGG. And the VGG is going to be used only as a loss function, right, to get the content loss. So before we can take this output and stick it into VGG, we need to stick it through our standard mean subtraction preprocessing. So this is just the same thing that we did over and over again in part 1. So let's now define this output as being this lambda function applied to the output of our upsampling network. Okay, so that's what this is. This is just our preprocessed upsampling network output. So we can now create a VGG network, and let's go through every layer and make it not trainable. Right? Like you can't ever make your loss function be trainable. Like the loss function is the fixed in stone thing that tells you how well you're doing. So clearly you have to make sure VGG is not trainable. Alright, now which bit of the VGG network do we want? Well, you can try a few things. I'm using block 2 conv 2. Okay, so relatively early, and the reason for that is that if you remember when we did the content reconstruction last week, the very first thing we did, we found that if you could basically totally reconstruct the original image from early layer activations. Whereas by the time we got to layer 4, block 4, we got pretty horrendous things. Right? So we're going to use a somewhat early block as our content loss, or as the paper calls it, the perceptual loss. Right? And you can play around with this, see how it goes. All right, so now we're going to create 2 versions of this VGG output. And this is something which is, I think, very poorly understood or appreciated with the Keras' functional API, which is any kind of layer, and a model is a layer as far as Keras is concerned, can be treated as if it was a function. Right? So we can take this model and pretend it's a function, and we can pass it any tensor we like. And what that does is it creates a new model where those 2 pieces are joined together. Right? So VGG2 is now equal to this model on the top, and this model on the bottom. And remember, this model was the result of our upsampling network followed by preprocessing.
In the upsampling network, is the lambda function to normalize the output image?
Yeah, that's a good point. So we use a fan activation, which can go from -1 to 1. So if you then go that plus 1 times 127.5, that gives you something that's between 0 and 255, which is the range that we want. Interestingly, this was suggested in the original paper in Supplementary Materials. More recently, on Reddit, I think it was, the author said that they tried it without the fan activation and therefore without the final deprocessing, and it worked just as well. So you can try doing that. If you wanted to try it, you would just remove the activation and you would just remove this last thing entirely. But obviously, if you do have a fan, then you need the output. And this is actually something I've been playing with a lot of different models. Anytime I have some particular range that I want, one way to enforce that is by having a fan or sigmoid followed by something that turns that into the range you want. It's not just for images. Okay, so we've got 2 versions of our VGG layer output. One which is based on the output of the upscaling network, and the other, which is based on just an input, right? And this just an input is using the high resolution shape as its input, right? So that makes sense because this VGG network is something that we're going to be using at the high resolution scale. We're going to be taking the high resolution target image and the high resolution upsampling result and comparing them, right? So now that we've done all that, we're nearly there. We've now got the high res.
So let's see. We can stop here, or we could try to finish this.
He doesn't take his break even up to. He
I
must.
can't remember when he had a break. I watched it to 120. I can't remember when he had a.
There was one point where there was a bit of a little bit of a jump, what felt
Yeah.
like a jump.
I think that's
And he
the story.
said, and he said, I was just having some interesting discussions over the break. So I think
Yeah,
that,
cut out.
yeah.
They may have just cut out the break,
Yeah.
the invocation.
That was the last
Yeah.
video. So
What time did we add in the video?
107 flat.
Oh,
Okay.
Artistic style was just my sneaky.
whoops. It
Went back to your old
went
spot.
back to my old slot. Wow, weirdness.
Target image and high resolution upsampling result and compare it.
I'm okay with stopping there.
I'm okay.
Yeah, that's
Yeah.
cool.
We're gonna recap kind of what the model looks like and see the results next time. I think that works well.
Yeah, I think I'd like to read that paper actually. This is all based
And
on.
release the half of a video. So
Yeah.
you should be happy.
I'm just gonna post on Slack.
Yeah, that was the whole. That was.
That
Nice.
Can you find your way to Camtasia and stop it, or maybe Duffy can stop it?
If you have watched till this, is it still?
It is, but I'm just about.
If
to
you
turn
have
it off.
watched till this moment, post on the Slack what minute we ended on.
Final test.
Final test.
Andrew, how far did we make it?